Welcome to another GCBASIC demonstration. This is looking at program memory operations for the AVR DX, September 2024. Let's get started. So I'm using a C Nano board. You could use any of the AVR DX chips, so that's 3217 range, etc. Many different chips to support this. So what we're going to do is we're going to write to what's called flash code. And the flash code is a good place to store data when you have used up the EEPROM. Let me just pick up a pen. So this is what we've written before, the EEPROM area. We can obviously use the RAM area. That's the RAM there, sorry. The RAM there. But this is all about writing. I will just get rid of my... Okay. This area here. And it might be useful because you've run out, because your EEPROM space 256 bytes, maybe you need more than that, so you're going to write data into here. And of course, there is a bit of a problem with that, is that that's also where your program lies. But we'll discuss that in a moment. So what we're going to do is use a function, instead of two functions of writing and reading to this particular area on these chips. So first of all, we have to talk about fuses. There are two fuses that impact this. If you don't set them correctly, you will get no write, and then you'll get an error. And they are called boot, end, and append. And they have different values. And we're not using a bootloader because we write raw code. And it is extremely confusing how Microchip have sort of assumed everyone's using a bootloader. We don't use bootloader, we just write directly to the chip, that's fine. So we just need to understand how boot end and append fuses impact this. And so the boot end determines what's called the end of the bootloader section, and then the append is where your application sits. And it sort of makes sense if you, in that context, that if you've got a bootloader, you're going to load a program on top of that. Now, historically, the bootloader was at the top of memory. Now, for some reason, they've assumed it's at the bottom of memory. And so I've got a little diagram that might help. So on the left here, this is what they've assumed, that you've got a bootloader. Oh, let me just go back and pick up my pen. You've got a bootloader. And then when you run the bootloader, it puts your application code in here, and then you've got some application data, and they're separate areas. And so the boot end sits here, and the append, the application end, sits there. But of course, we don't have that. What we've got is GCBASIC program sitting, starts at the bottom of memory, and then you've got application space. You've got stuff, empty space, basically, and you can write to that space. What you can't do, you don't want to be writing into here, quite clearly, bad practice. And so what we're going to do is we're going to set the bootloader value to here, and we're going to set the append to here. And that way, it just works. Now, there is a bit of a problem with this, is that you just need to figure out the size of the program. Well, that isn't hard to do because that's reported back. Or you can set this level quite high. You could set it right down here and only have a block of memory down there. It's up to you, but you've got to set the fuse. A fuse of 00 will not work. You need to set the boot end so that you've got some access. I'll explain more. So in this particular chip attached to here now, I've got it set to the bootloader is set to page B, which is quite large, and I've got append at FF, that's the top of memory. So it basically means I've got this huge block where I can sort of write to. Then you might want to set your append to your boot end to FE and just leave yourself 128 bytes at the top of memory. I don't know, it's down to you what you do, but you must set the append and boot end. These are set to 0. You won't get any write. I'll explain why. Why? Because the intersection write protection between these areas of boot, app code, and app data is very clear. Code in the boot section can write to the app code or app data. App code can write to the app data, and app data cannot write to flash or EEPROM. So if your program sits in the app data area because of your fuse has been set incorrectly, you will get no write operations. And if you don't have a bootloader set, a boot end set, you don't have an app codes area or an app data area. Therefore, you cannot write to them. So setting this fuse is very critical. But once you set your fuses, everything is quite simple. You can write and read bytes, words, strings, data. You can actually do a lot more than that, but I'm just going to show you those today. Let's go straight into some code. So let's zoom in. Oh, here we go. I am doing some coding. Here is some code. All I'm going to do is use this function here, PROGRAMWRITE to an address with a value, and it's a byte value in this case. And the rest of this is just getting it all on the screen. And then there is another function here called PROGRAMREAD, which actually goes and gets the value back. So it writes it to an address, and it actually pulls it back. It reads it back into a new value and puts it on the screen. So if we do this, it's very simply explained. So I've set an address of B000, my value is 5, and you'd pull this in. This could be configuration values or taken in via some sensor for data logging. It'd be great for data logging. And essentially you write, then you read it back, and there's a little variable called NVM control status counter. If it's non-zero, there's been an error and you can handle it. Function key F5, I'm just programming it. Let's go out to a terminal, pull it in. And it says here, change set to byte in program memory. Well, that's what was in our source program. Byte value written to program memory is 055. There we go, 0x55. If I change it in the source, I pressed, I think, function key F5, and it's just programming it. And it's actually changed that to A8. Very simple. I wish it was that simple when I was programming it. Let me just look at another program. I'll just pull up a word demonstration. Very similar. This is all the preamble. I'm not referring to, for instance, how you set up the chip or the USART. This is going to, well, this should say change a word in program memory. Great. I'm going to write it to the address B00 again, but I'm going to put 1234 in. And then I write out my low byte, I write out my high byte, and then I get it back as a word. Let's have a look at that. Program, oh, there we go, 1234. How do we know it's working? Well, let's start up Microchip. This is Microchip Studio. I'm going to open up an existing project, and I've created a project for the 4809 in here. It's just an assembler project, and I'm going to take my assembler from GCBASIC, and I'm just going to put it into there. So function key F7, Control A, Control C, and I'm just going to paste it into my source program. And you might not be able to see this, so let me zoom in. This is my empty program. I'm just going to paste that in there. There we go. And essentially what I've just done, I've just taken the source from GCBASIC and put it in there. And I'm just going to program it by pressing function key F5 or running it. And it opens up loads of dialog boxes. But one that you want to have a look at is if you select at the top here, a window, was it debug windows, and you select, which one is it? Well, I'm so sorry, memory. You can end up with this window here. I'll pull it up there for you. We can then look in the program memory. Now, whilst it's running, we can't look at it. So if we just pause there we go, pause it. There's the program memory sitting there. Look, we're looking at the program memory. So if I type in here, the address I used, B000, and hit enter. Now, was that the address I used? There's my program. I'm just cursoring down. Yes. Oh, there it is now, look. Sitting in the middle of memory, look. There. 1, 2, 3, 4. That's what we put in the program. Let's have a look in our source program. In our source program here, in the word here, I set it to 1, 2, 3, 4. So that's correct. It's done its stuff. So it writes it out. Quite hard to find it in the debugger here. I don't know quite why I didn't get it. Oh, there you go. 1, 2. I did it correctly this time. So it's put it in memory. We can do we just stop the debugger there. We can do the same for a string. This is a string, and all I'm doing here is I've created a string in the program. I've said my string is that. Then I just iterate through it using a for next loop, and I say, write that out to an iteration. So I'm just adding the value of my iteration index into the program memory, and then I get it back. And just for those who don't know, a string of index 0 is its length. And therefore, if we write it out to put the program memory out, and we index through, then we get each character and we can put it in memory. So let's just run that, and we'll see what happens on the terminal, and then we'll have a look in the debugger. And it says here on the screen. Let me pull that up. Writes a string in program memory, GCBASIC 2024. Okay, let's pretend we don't believe it. Back into the Microchip debugger. Run it. Now, why am I waiting a second? Because there's a few delays on there, so I'm just going to wait for it to make sure it's done the right operation. And here it is. It says it here quite clearly. There's the first byte is the length of the string, and it's written it into memory. And it writes the whole block, so it handles all the block stuff. And so you need to write a page out. That's fine. Last one. So I'm going to write out a data block. And a data block is something like this. It's a whole set of data, reference data. I've written out 28 bytes, and this one happens to be lorem ipsum. So all it's going to do is iterate through the 128 bytes. First of all, we can prove it's done it because we can see it in the terminal. In our debugger, let's just run that. You can see there's the data block sitting there in the program memory. If I just stop that, we can now see it's updated page B00, and there's the whole page sitting there in memory. Now, obviously, it's further in memory. This is not how you would do it. This is just a way of creating programs with reference data. It's just an example for you. That's absolutely great. So it's very simple. In recap, there are two very simple functions: program write and program read, and they just go and get byte values in and out of memory. I guess with program read, you can use it throughout the whole of memory and then move things around, but it's a great use case. So with that done, enjoy.